Now, real talk, guys, with chapter 10, probably the second hardest thing we do in second semester, behind the vector stuff. The good news is that after this one, though, everything else that we're required to get through, I think, is going to be pretty familiar. Is either going to be like review or minor extensions of things that we did in Algebra 2 last year. So if you felt pretty good with your Algebra 2 stuff, things should get a bit easier here pretty quick. But this one here is can be kind of tough. Everybody okay with that, though? Just as a heads up. In particular, I think today is maybe the toughest day. So in chapter 10, we're going to talk about parametric and polar functions. And we kind of split that pretty much evenly down the middle, where the first half of the chapter is the parametric pieces and the second half of the chapter are the polar pieces. So today we're going to just start by talking about parametric functions, and then we'll talk about applications of parametric functions afterwards. And then we'll do kind of the same thing with polar stuff. Okay. So up until this point, all the functions that we've talked about would be classified as, come on. All the functions up until now we would call Cartesian functions. In the sense that we have an x and a y, where the x is our input and the y is our output. Can you remember our definition for a function that we've used? Okay, yeah, that's basically it. Let's formalize that a little bit. So we say that a function is a set of ordered pairs where every member of the domain pairs with exactly one member of the range okay, and it's that exactly one part that's really the important part there. Is that ringing a bell? And how did we, what was the easiest way to check to see if something was a function or not? Yeah. We could use a vertical line test. So under our Cartesian setup, something like a circle was not a function because we have a situation where we have one input that has two different outputs, right? Does everybody feel okay with that? Well, what could we do if we wanted to have stuff that failed a vertical line test be a function and still meet that definition? What would we have to do if we wanted things to still meet our definition of as a function, but not necessarily have to pass a vertical line test? Let's think about that for a moment. So we want to still be a function, but we don't necessarily have to pass a vertical line test. So in the Cartesian sense, when we talked about our function, we had to have like these sets of, or these pairs of x, y's, right? Well, if I wanted to, what I would end up doing is my new ordered pair would be some parameter as the input, and the output would have to be the xy point itself. So what was our input and output as an x and a y, here the input is some parameter, and the output here could be an ordered pair. And if we're able to create such a function, the inputs have exactly one output, where the outputs are ordered pairs, and those ordered pairs need not pass a vertical line test, because my inputs aren't x's anymore. My inputs are this parameter t. And that's exactly what we're going to do when we create these parametric functions. So there's still, the parametric function still fits our definition of a function, but that vertical line test need not apply anymore. So our parametric function is going to be a function in terms of t. So this parameter t is going to be our independent variable. And our x and y coordinates are going to be equations that are being based on t. And then we're going to have to define t over some interval. So we're going to have to state explicitly what values of t are we allowing or not allowing. So just as the vocab, f of t is our parametric function. X of t and y of t are parametric equations. Our t is our parameter. And the I is our parameter interval. So like we pick a value of t, and when we plug that value of t into our two parametric equations, that's going to generate us the point that we would plot on our xy axis. So the t is not plotted anywhere. It's kind of like a hidden lurking variable or whatever. Is everybody okay with that? We refer to it as a parameter to differentiate it from like a variable or a coordinate. So let's do a couple of examples here to kind of get a feel for what's going on before we kind of get too much more in depth. So the point of this example here is just to kind of illustrate to you the importance of the parameter interval. And we're going to just use our graphing calculator here to generate the pictures for these graphs to just kind of show you a picture and show you exactly kind of why we care about these parametric functions and what we're capable of doing with these easily that we could not do easily or could not do at all with a Cartesian function. So if you want to follow along and you have your graphing calculator with you, I invite you to do so. If you'd rather just sit and watch, you're fine to do that as well. Whatever works for you is okay with me. So the first thing we're going to do is we're going to press our mode button, which is there right next to the blue second key. Now notice this fourth line where it has four options. It has func, par, pol, and seq. FUNC is like Cartesian functions. That's everything we've done up to this point has been in the Cartesian function. We're going to start graphing some parametric things, so I invite you to go and activate option 2 where it says PAR, which is short for parametric. POL is short for polar. We'll talk about polar functions later this chapter. When we do that, we'd have to change our option again in the mode menu to this polar setting. And then there's sequential. So if we're dealing with like sequences and trying to do like plotting sequences or something, we could use that mode as well. But we're going to change it to PAR. And if your calculator is still in degree mode, which it probably would have been from last chapter, let's go ahead and turn it into radian mode. When graphing things, oftentimes the radian mode is going to be a little bit easier for your calculator to handle because, well, 2 pi is a heck of a lot smaller number than 360. Okay. So if we press the y equals button now, our y equals menu looks much different than it did before. Notice that in each of these we have an x1 of t, a y1 of t, etc. Because the parametric function has 2 parametric equations, one for x and one for y. So if I want to graph this, I'm going to put in place of x1 of t, t squared plus 1. If you press your variable button, which is right next to the green alpha t, or alpha key, you'll notice it gives you a t automatically because the independent variable in parametric functions is t. So you don't have to do anything different once you've changed your mode to get your t in there. So there's that. Is everybody okay with how I did that? Okay. Ooh, excuse me. Next thing I'm going to do is I'm going to go to my window. So there's two things that I'm going to check. I'm going to start by just resizing my X and Y window to make sure it's kind of the standard -10 to +10. It's likely that could have been mucked around with, or I'm not sure if your calculator saves your function window and brings it with you to the parametric setting. I kind of doubt it. Probably most of your guys' X and Y mins and maxes were -10 to +10. What we do need to change, though, is the Tmin and Tmax. So for part A, my Tmin should be -infinity and my Tmax should be +infinity. Now, obviously, we can't put -infinity and +infinity into our calculator. And in fact, just picking an absurdly large value for the Tmin and Tmax is probably a bad idea too, because you can really overflow your calculator pretty easily by doing this. All I really need to do is be able to fill the screen. Since my X is only going over to -10 to the left and +10 to the right, and my X coordinate is t² + 1, it feels pretty safe to just do -10 to +10. Will fill the whole screen for me. Everybody feel okay with that? If I look at the Y, the same thing would be true, right? If my Y is going from -10 to 10 and the Y is 2t, -10, 2 times -10 and 2 times +10 will certainly cover all the Y values in there. So the TStep, I don't know what it's set at. This is the number that I have. The TStep doesn't really matter. You want it to be like small, but not like stupidly small. Like it'll just take a long, long time if it's really, really small to graph it. And if it's too big, you won't get a very good resolution on your curve. It'll look kind of chunky or something. So, but this number I have is fine. I think this is actually pi/24 is what it looks like to me. Let's try it. Pi divided by 24. Yeah, that's what that was. Anyways, let's hit graph and take a look at what we get. So I get this sideways facing parabola. Was this something you could have graphed in the function mode with one line? No, you could not have, right? Because in the Cartesian sense, or as a Cartesian function, this would not be a function, right? In the Cartesian sense. Although as a parametric sense, this is a function. You guys see that? That's why the vertical line test is kind of meh, because it depends on what kind of function you're talking about, whether we want to count that or not. Okay, so let's look at part B now, where we're going to go from -3 to 1. So I'm just going to go back to the window, change the Tmin to -3 and the Tmax to 1, and then hit graph again. What do you notice? We're just getting a segment of the previous picture, right? Is this still, does this pass a vertical line test, though? No. Would the domain and range of this function be the same as the previous one? No, right? Both the domain and range would be different than the previous. Even though you're graphing the same curve, that interval of the parameter definitely makes a difference there, right? Let's change it again to -1 to 2. Hit graph again. It's a different section. If I change it from -2 to 3, oops, -2 to 3, I get a different section again. Everybody's okay with this? Do we see how how we're generating the points there? For example, you're plugging in -2 in for t, so the first one you get the point 5, -4. That's this one. And if I plugged in the other endpoint, you get 10, 6. That's this one up here. And in between, you're generating all those points in between. Does that feel okay for the t's in between those two endpoints? It's kind of how this is working. Instead of picking an x and then plugging it in, finding the y, you're picking a t, plugging that in, and you're getting x and y. Okay? Let's do another example here. I guess I'll call this now. In a sense, you guys are already kind of familiar with a parametric function. I guess it doesn't really matter. Do that. What if we wanted to say graph this guy? Before you type this into your calculator, we've seen this already in this course. What do you think this picture is going to turn out to be? It's not going to be a wave. It's what? The unit circle. Remember, the unit circle had coordinates cosine theta, comma sine theta, where the values of theta could go from 0 to 2 pi. This is exactly what we're going to see here. So if we go and type this into our calculator, we're going to do cosine t to sine t for our x function, y function, or x equation, y equation, I should say. And then our window, I'm going to change this t min to be 0 and t max to be 2 pi. And just so I can get my circle isn't itty bitty teeny weeny, maybe I'll change that to like -3 to +3 or something for my scales. But there we go. Now, if you had forgotten to put this into degree mode, what would have happened? You'd have basically gotten like a little tiny section like this, because you just graphed from 0 to 6 degrees of the unit circle, which isn't a whole heck of a lot. So to fix that, you could either go in and make the 0 to 360, or you could put your calculator back into radian mode. I would just put it into radian mode, but, you know, either is okay. You'll get the same picture. Okay. Everybody okay so far? Okay. So we have now these two different kind of types of functions. We have Cartesian functions, and then we have parametric functions. Kind of the normal thing we'd want to do is talk about how to go back and forth between them. To go from parametric to Cartesian, the direction we usually say is eliminate the parameter. And to go from Cartesian back to parametric, we'd say to parameterize. And right now we're going to talk about this direction. The second part of this lecture we'll talk about going from Cartesian to parametric. But first we're going to go from parametric to Cartesian. Okay? So we're going to do a couple of examples of this. And this first example is I'm going to be very detailed. And as we go, I'll probably carve off some of the details so it doesn't take 15 minutes to do the problem, like it's going to the first time we go through and do this and talk about some of the hypothetical little spin-offs and make sure we really kind of explain thoroughly what's going on. So when we say eliminate the parameter, really what we want is we want a y equals equation at the end, right? Like the thing we're normally we're used to seeing. So what we do is we start with the independent variable. Instead of writing that as x of t, I'm just going to write it as x. And I'm going to just get the t by itself. Is everybody okay with that? Not a big deal. Then we're going to take the equation for y, and I'm just going to, again, rewrite that with just a y. I'm going to drop the y of t. And then we'll substitute in our value of t that we found and simplify. Is everybody okay with what we've done there? However, we're not finished. If you refer back to our first example, when we looked at the graph of this guy here, depending on which interval for our parameter we considered, we got four different graphs that would have had 4 different domains and ranges, right? They really represented 4 distinctly different functions. So we're not done with just given the equation. We also need to make sure we give the domain and range for this. And this is the challenging piece, okay? What we're about to do in finding these domains and ranges is not trivial, especially initially, okay? So this requires some good close attention. So if you've kind of drifting on me, try to focus in the best you can, okay? So when we talk about, okay, let me actually start a little bit in a different place. If I just wanted to talk about the domain and range of this y equals 1/3 x plus 1/3, if it was not coming from a parametric function, if it was just like, what's the domain of this? What is the domain and range of y equals 1/3 x plus 1/3? Should be pretty trivial for students at your level to do this. Okay, what type of function is this? Give you some hints. Lily?
Is it just negative?
Good, the domain and range actually are both all real numbers. Correct. This is a linear function. It's the equation of a line. So like it's a line with positive slope, so just going up from left to right. So we have one arrow pointing down and to the left, the other arrow pointing up and to the right. That's covering all the x's and all the y's, right? All real numbers. Let's see what the domain and range is if we actually are taking the parametric function and see what we have. So when we talk about the domain, that's coming from which coordinate, x or y? Okay. The x. So the x coordinates of our Cartesian function are generated, or are the outputs of, the parametric equation for x. Everybody's okay with that? Now, if the outputs of x of t give us the x coordinates for our Cartesian function, y equals 1/3 x plus 1/3, the inputs are the parameter, or the interval for the parameter. So that tells me then the range of x of t, our parametric equation for x, is the domain for our Cartesian function, y equals 1/3 x plus 1/3. So if I look at this equation for x of t, what type of function does this represent? Should be a trivial question for students at your level. Lily? It is a linear function, right? Just looks like mx plus b. Everybody's okay with that? If the domain for that linear function is all real numbers, what's the range have to be? Also all real numbers. Is everybody okay with that? If the line's extending in both directions to the right and the left, and it's kind of going up and down, it's got to cover all the y values as well, right? And since the range of x of t is all real numbers, the domain of our Cartesian function is also all real numbers. Do you suppose that's frequently the case, that the interval for the parameter is the same as the domain for our Cartesian function? No, it's not common. We'll take a variation of this problem in just a second and show you specifically how different things can get. Okay. Let's talk about the range now. I'm trying to be really clear when we talk about domains and ranges here about like which specific thing we're talking about a domain and range of, right? Am I doing a good job of being specific enough? I'm trying really to write everything out and not be too hand wavy here, because I know this is not trivial. This is hard what we're asking you to do, because you're like walking through some different definitions and using a lot of previous skills. When we talk about the range, which coordinate are we talking about? Y. We know the y coordinates of our Cartesian function are the outputs of the parametric equation y of t is equal to 1 minus t, where the inputs are negative infinity to positive infinity. So this says again that the range of y of t is going to give us the range of our Cartesian function. So if I look at that function y of t, what kind of function do I have? Linear. If the domain of that linear function is all real numbers, what does the range have to be? Also all real numbers. Oops. Okay. What I'm going to do now is I'm just going to take this same exact problem and I'm going to change that interval for the parameter and show you how our process changes when we do that. Okay? Everybody ready? All right. So all we're going to do is go back up to our example. And I don't know, let's make that go from -4 to 2. So I'm just going to kind of take the same, all my work here, and I'm just going to kind of alter within green this different version of the same problem. We'll just do some work off to the side to show the other hypothetical on kind of what we're thinking about and what we're doing here. So we have our same function x of t, still a linear function, right? Specifically, what can I say about the linear function x of t? Its slope is -3. The y-intercept is 2. So if I were to sketch a picture here, it starts at some point -4 and then x of -4, and then it slopes down and it ends at some point 2 comma x of 2. And again, the axis here is a t x of t. And what we're graphing is x of t equals 2 minus 3t. And this is not at all to scale. I just kind of drew a picture to help us visualize what's going on. Is everybody okay with the picture that I've drawn here, what we're representing? So what we have here is a line segment, right? That's our equation x of t is representing a line segment now. So if I want the range of this, basically I just need the minimum y value to the maximum y value. Oops. 2 minus 3. Is everybody okay with that? So my range would be that x of t goes from -4 to 14. And because because my interval for the parameter was closed at both ends, right? I had brackets on the -4 and a bracket at the 2. I know that the number or the y coordinate associated with the -4 should have a bracket on it, and the y coordinate associated with the 2 should have a bracket on it. So that's what the domain then for my Cartesian function would be. Do we feel okay with what we've done here? Do you need a minute to just process? Should I pause? Do you need a repeat? Do you have a hypothetical, a clarification? I'm trying to go very slow through this because I know it's not easy. So if there's something that's going on, stop me and ask, okay? You all are encouraged. I'm giving you permission right now. All right, we'll keep going then. So same idea here. So we still have our linear equation, y of t equals 1 minus t. Again, that's negative slope, y-intercept of 1. So one endpoint is going to be -4, y of -4. And the other end is going to be 2, y of 2. Again, I'm looking for the range of this function. So I'm really just going from y of 2, the minimum, up to y of -4, the maximum. So going from -1 to 5. And since -4 was included, had a bracket on it, the coordinate 5 that comes from -4 gets a bracket. Likewise with the -1. So our range then is going to be -1 to 5. Does that feel okay? Mr. Kulik, does it get worse than this? I mean, only in as much as the functions you're dealing with could get more complicated, but the process will remain largely the same. Let's do another example where that happens. So here's our new parametric function. F of t equals x of t equals negative 4t, and y of t equals 2t squared plus 1. And the interval there for t goes from negative 2 closed to positive 4 open. Remember, the bracket means that that negative 2 is included in the set, and the positive 4 is not included in the set because that has a parenthesis. Everybody's okay? So right away, hopefully you notice kind of two things should stand out to you when you look at this. Do you guys notice anything here that's decidedly different as a detail than the previous example, Lily?
The y and y of t squared.
Yeah, so we have a different kind of function for our y equation. Very good. And what else? The x function doesn't have a y-intercept, but that's okay. It's still linear. That's not really going to change much for us. The other thing we'll have to be careful about is that our interval for our parameter isn't closed on both ends. So we're definitely going to have to be careful about that as well, that that's a parenthesis there. Maybe I didn't do a very good job with my neatness. Okay. Well, the start doesn't change. And at this point, you're probably thinking, yo, Mr. Kulik, this is no big deal. I got it. We're done, right? Oh, no. Sweet child. We must worry about the domain and range part. That's more typically going to be the more challenging piece. Eliminating the parameter is usually fairly straightforward. Make a little spot to write down our answer to go with it. Okay. So the domain, which parametric equation do I need to look at? The one for x. Very good. What type of function is that x function? It's linear. So we have, oops. Yeah. So we have something like this, right? So again, pretty straightforward. The range is just going to go from the minimum to the maximum. Or from the low point to the high point, right? When I say min and max, that's what I'm talking about. So I have this. So we're going to go from negative 16 to 8. But because 4 has a parenthesis, the y-coordinate, or I should say the x of t coordinate, associated with the 4 also needs a parenthesis. And then since the negative 2 has a bracket, the x of t coordinate associated with the negative 2 also gets a bracket. So this will be the domain then for my Cartesian function. Not a big deal, right? Still basically the same as before. We have to be a little bit careful about making sure we have the parenthesis in the right place. Notice that it kind of switched ends, right? Instead of ending with a parenthesis, our domain for our Cartesian now starts with a parenthesis, but that's okay. That can happen. Will it always happen? No. But it can. All right. The range. As Lily already identified, we have a t squared in the range. What type of function is this? As a name, right? Quadratic, very good. What's the shape of the graph for a quadratic? Parabola. Okay. Do you guys remember, can you tell me anything about the shape of the parabola for 2t squared plus 1? It's opening up, very good, and the y-intercept is at 1. Okay, so, oops, let's write that down here first. Okay. So, there's two possibilities, right? One of them is that we have something like this. Oops. Where the vertex is in between our endpoints. And again, this is a t, y of t function. Everybody's okay with that? The other possibility is that, like, this. Let me draw this the way I want it to first. Oops. Is that the vertex maybe is not in between, or not on the interval for our parameter? Jacob.
You switch to the -4 to less.
Oh, did I do? Oh, sorry about that. Wish you would have said something earlier. All the typos. Thank you. If you see me writing stuff down wrong, don't wait. Even if it wasn't a mistake, Mr. Gulick would never yell at you for asking a question about something that you think is a typo, or you're like, hey, I don't know why you did this. It saves me having to go back and make 100 edits. Okay, so it's going to be one of these kind of two situations, right? Either the vertex is in between the 2 points, or the vertex is outside of the 2 endpoints. Now, if it's this situation, we just can do the exact same thing we did before, right? Because the minimum and maximum are just the endpoints of our function. Do you guys agree with that? What we have to be careful about is that if it's this first situation, because then the minimum is actually at the vertex, and the maximum would be like up here. So what do we have to find in this case? We got to find the vertex in order to tell whether it's inside that range or inside the interval of the parameter or not. Who remembers how to find the vertex of a parabola? Not the calculator. actually, we'll just grammar this up. The is okay. So the vertex of the quadratic function f of x equals ax squared plus bx plus c is negative b over 2a, comma, f of negative b over 2a. If you don't remember that, you may want to write that down, as it'll come up not infrequently in the homework. So in our case, the vertex, we'd say t, that's our independent variable there, is going to be 0 over 2 times 2, or 0. Everybody's okay with that? Now that is definitely inside the interval for our parameter, right? 0 is between -2 and 4. So we do care about the y of 0 then. So that's 1. Yes, Taylor. It's the b value, right? There's no b value because there's no linear term in that quadratic. Yep. Totally cool to ask about stuff like that. If I do something that I assume that we all got and you missed, please speak up. Doesn't mean that you weren't paying attention. It just means that we scooted past something that I took for granted that you didn't take for granted, and that's okay. All right. But we also need the endpoints as well. So we'll do y of -2. That gives me 9. And then y of 4, which gives me 33. Oops, 4. Okay, so now I'm going to consider those 3 points. So the smallest is the smallest is 1, and the biggest is 33. Everybody's okay with that? Since 0 is inside that interval and 1 comes from 0, I know 1 gets a bracket. Because 4 has the parenthesis, 33 should get the parenthesis, so my range should be 1 to 33. Is that okay with everybody? Of course, yeah. Super hypothetical. What if we had the parenthesis was reversed? So instead we had this. Now, you'd think probably 1 to 33, right? Both inclusive because we have 0, 1 here, and then we have 4, 33 over there. This is negative 2, 9 over there. Everybody okay with that? Does it matter that 9 is open and 9 is in between 1 and 33? What do you think? In this case, no. Why not? No, because there's another point, specifically this one right over here on the horizontal line, that uses the y-coordinate 9. So 9 is used somewhere, not at that endpoint, but that's okay. It's used somewhere else, so we still get to count it. Does that make sense? If you had something like that, that would be the other way you would want to, maybe you would have considered writing it. Not in this case, though, as we illustrated why, because the 9 is used somewhere else. It's used not ever. The 9 is a y coordinate somewhere, just not at the endpoint. But that's okay. It doesn't need to be used specifically at the endpoint. Let's look at another situation where we might have to do, we do have to do something a little bit different. Yes, Sergio. Sure. No problem. Okay. Oops. All right. So probably just, like we'll start the same way, right? So we divide by 3. And I guess we'd have to do the cosine inverse of both sides. Oh, boise, I'm not liking the way this is looking. And I guess we plug this back into the other one. Yeah. What would we even want to do with that? Yeah, that looks gross. What should we do instead? I don't like that. Do you like that? I got a nested cosine inverse inside of a sine function. Woofarooskies. I couldn't even guess what that was supposed to look like. Instead, I'm just going to look at a picture. In fact, my calculator is almost all the way set up to do this. So what type of shape did I get there? Okay, are you sure it's a circle and not an oval? Looks a little oval-y to me. Is this a circle or an oval? Who can tell us? There's a definitive answer, and you have everything you need on the screen to tell you. It is a circle. If you notice that if I count on the x-axis, the radius is 3 on the x-axis or on the y-axis, and it's also 3 on the x-axis. Why does it look like an oval on my screen? Your window is rectangular. Yeah. The calculator screen is rectangular. You write a letter to Texas Instruments and tell them to get with the program and stop writing a distorted calculator screen. Okay, so we have a circle. What else can we say about that circle? What other two attributes can we say about this circle? If you're describing this circle to me and I was supposed to draw a picture on the XY axis, what two things would you have to tell me? Lily.
Its radius is 3.
Great. The radius is 3. And then there's one other thing you need to tell me. If I was able to, you wanted me to draw this picture on the XY axis. Lily?
It starts at 0.
The center is at 0, 0, the origin. Right? If I knew those two pieces of information, I could draw a picture of that circle, right? I wouldn't have to see the picture you're looking at if you told me circle, radius 3, center 0, 0, should all end up with the same picture. If you gave me any second piece of information other than the center, you could get multiple different circles. If you just gave me some other point on the circle, you don't know whether, which way to draw the circle from. Okay. Who remembers the equation for a circle from geometry? Again, not an unreasonable request for students at this level. So the equation for a circle with radius r and center hk is x minus h squared plus y minus k squared is equal to r squared. So in our case, what would we have? X squared plus y squared is equal to 9. Okay, sure, fine, no biggie. Do you think that's sufficient, just looking at the picture and writing down an equation? We should check this to make sure. How do you suppose we're going to do that? Lily? Well, we're going to plug in the parametric equation for x and the parametric equation for y and see if indeed that does give us 9. So 3 cosine t times 3 cosine t gives me 9 cosine squared t. And 3 sine t times 3 sine t, again, is 9 sine t, or sine squared t. What do you notice now? Well, I see that they both have coefficient 9. So I'm going to go ahead and factor that off. And John says the Pythagorean identity, cosine squared plus sine squared is 1, which is definitely equal to 9. So this thing is super correct. What do you guys think?
What that equation we were checking, that's the equation for our circle?
Yep.
And the circle is
that was the picture we got from the calculator.
okay. So we haven't done the domain and range yet. That's just started.
And you know what? For a problem like this, the domain and range are kind of obvious, right? You just read them from the circle. But here's the neat part, is that given a circle like this, you don't even really need to give the domain and range. It's implied from the, yeah. If you wanted to, we could write it down, -3 to 3 for both. That's fine. Okay. Yes, sir. So we've gone from parametric to Cartesian. let's talk about going from Cartesian to parametric. So let's say we wanted to parameterize y equals 3x minus 2. Does this pass a vertical line test? If that's the case, the parameterization is super simple. In the Cartesian form, the independent variable is x. Trivial question for a student at your level. In the parametric form, our independent variable is t. So I'm just going to go ahead and set x of t equal to t. If I do that, then y of t has to be just 3t minus 2, the same thing as our function above. And since our t is equal to x, the domain from the Cartesian is going to be the interval for the parameter. What's the domain for y equals 3x minus 2? All real numbers. It's just a line, right? And I'm done. No calculation to do. Could you do this other ways? Yeah, but why would you? Taylor.
Well, why does x equal t? Just because they're both in.
So as long as your Cartesian passes a vertical line test, you can just set the independents equal to each other, and then your function in terms of x just becomes a function in terms of t as your y equation, and the domain becomes your interval parameter, and you're done. There's just it's the simplest mapping you could possibly do. We have a couple more examples on this, but looks like we're about out of time, so we'll hit those next time. At this point, you guys can start working on 1 through 40. Here's the good news. Next time, we're going to finish the last 2 examples I have. Maybe do 10-2, depending on. Here's the nice part. 10-2 has 9 problems or something like that. It's short. And I wouldn't even put them on the problem set for Sunday because we wouldn't have had a chance to talk about them before then. So Sunday is just going to be 1 through 40. And on your virtual day, what am I going to ask you to do? Just work on your homework, man.
Are we having a homework quiz next class?
What?
Are we having a homework quiz next class?
No, not this week, man. We'll do it next week or something.
Sweet.
Okay.